Balloon 11-1 The gas balloon. Let's embark on an exploration of manned gas ballooning. Now, the realm of gas balloons shares a kinship with hot air ballooning, yet harbors distinctive characteristics. Throughout this discourse, we'll frequently draw comparisons to hot air ballooning to anchor our understanding, especially for those seasoned hot air balloon pilots among us. Our focus centers on gas balloons boasting an envelope volume of 1,000 cubic meters, a size that dominates major competitions. Helium and hydrogen take center stage in our discussions about lifting gases, always assuming we're dealing with the zero-pressure envelope type. For now, let's set aside super-pressure balloons and the intriguing rosier balloons, the gas-hot-air hybrids. Venturing into history, gas ballooning, once the aviation vanguard in the United States, has evolved due to the associated costs. Nowadays, gas flights lean towards training, competition, or record-breaking exploits, with short recreational gas flights trailing behind their hot air counterparts. And now, let's rewind to the genesis, the birth of gas ballooning just weeks after Jean-François Pilatre de Rosier and the Marquis d'Arlans soared in the first manned hot air balloon. While the Montgolfiers were entranced by hot air experiments, enter the Robert brothers and Jacques Charles, conducting their trials with gas balloons. Picture the debut gas balloon, a modest 13 feet in diameter, filled with what they called inflammable air. It achieved a net lift of 35 pounds, gracing the skies for 45 minutes, covering 15 miles before its final descent, attributed to a balloon rupture. See the visual aid, depicting an early style of a gas balloon. Interestingly, many terms from that era still resonate in today's discussions. Bolstered by this successful demonstration, Charles crafted a 25.5-foot diameter globe of rubberized silk, adorned with a net over its upper half. This net, tied to a loop around the bag's middle, suspended a car or boat-like contraption. Picture this, a ballet of sorts, where dropping ballast made the balloon ascend, and releasing gas through a valve initiated a graceful descent. Fast forward to December 1, 1783, Professor Charles and Nicholas Robert etched history with the first manned gas balloon flight. An odyssey lasting 1 hour and 45 minutes, soaring to 1,800 feet, and covering over 27 miles. On landing, Robert disembarked, while Charles, now flying solo, ascended to almost 9,000 feet. Imagine the balloon, initially flaccid on landing, gradually filling out as it rose, strategically releasing gas to avert bursting. Fun fact: Benjamin Franklin was present, acknowledging the military potential of balloons. Subsequent ascensions were not mere airborne escapades, they were scientific quests. Early experiments shaped the design, form, lifting capacity, and grasp of air's weight for gas balloons. Notable among these flights was the 1785 English Channel crossing by Jean-Pierre Blanchard and Dr. John Jeffreys. Picture their balloon, scarcely sufficient, jettisoning ballast, anchors, food, and clothing for the historic journey. In 1906, James Gordon Bennett, a newspaper magnate, sought newsworthy exploits and birthed a gas balloon race in Paris, France. This Coupe Aéronautique de Gordon Bennett, an annual spectacle sanctioned by the Fédération Aéronautique Internationale, FAI, crowns the most prestigious gas race globally. The hosting rights? Bestowed upon the country of the previous year's victor. Now, shifting gears, the Albuquerque International Balloon Fiesta, AIBF, unfurls the America's Challenge gas balloon race since 1995. A beacon of prestige and international participation, this race promises pilots extensive flights and grandeur beyond measure. Let's segue into the intricate world of balloon systems, categorized as netted or quick fill. The netted design, tracing its roots to the 18th century, envelops a spherical balloon in a diamond mesh net. Imagine the inflation ballet, laying out the envelope, deploying the net, and adjusting sandbags as the balloon takes shape. Enter the quick fill design, emerging in the mid-20th century. A natural shape envelope is framed by vertical and horizontal support tapes. The ballet here involves laying out the envelope, attaching the gondola, and orchestrating a controlled ascent as the balloon fills. Now, onto the lifting gases. Modern gas balloons favor helium or hydrogen, with occasional nods to anhydrous ammonia and methane. Helium, a monatomic, inert gas, often trumps hydrogen, being more stable despite offering slightly less lift. However, selecting a lifting gas involves a dance of considerations: compatibility, cost, lifting capacity, availability, locale, and inherent stability. In this gas-filled odyssey, remember that safety is paramount. Inflating or landing with hydrogen or methane demands vigilance against potential sparks. Lighted cigarettes, cigars, nylon clothing, and electronic devices are strictly forbidden. Launch areas should be restricted to essential personnel for long, competitive flights, where the stability of helium stands as a key advantage. And now, directing your attention to the visual, behold the Spirit of Springfield, a netted gas balloon. A marvel echoing the 18th century design, preserving a stable hemispherical shape amidst variable winds. Transitioning seamlessly to figure, witness the quick-fill design, a mid-20th century innovation. Picture the graceful rise of this gas balloon, its envelope embracing a natural shape, stabilized by vertical and horizontal tapes, embodying the evolution of aeronautical engineering. As we delve into the intricate components of gas ballooning, let's explore the fundamental elements that constitute a gas balloon system, categorizing them into 4 key parts. Beginning with the envelope, it takes center stage as the vessel containing the lifting gas. Positioned at the apex of the envelope is the maneuvering valve, a critical component depicted in figure. This valve enables the controlled release of a small amount of gas to initiate descent, ensuring a carefully orchestrated maneuver. Its spring-actuated mechanism, controlled via a line running through the envelope into the gondola, adds a layer of precision. Variations, such as a gas-tight parachute top or deflation ports, enhance adaptability during high wind landings. Transitioning to the gondola, shown in visual, we encounter a space designed for both functionality and comfort. Larger than gondolas used in sport hot air ballooning, it typically measures 4 by 5 feet. A foldable cot or sleeping pad lines the gondola's long side, with a kick-out panel providing additional legroom for periods of rest and sleep. Externally, a trail rope, an essential element of about 150 feet of natural fiber rope, is used in specific landing maneuvers. Support cabling, the invisible yet robust connection between the envelope and gondola, is vital for maintaining structural integrity. Whether composed of rope, flat tape, or steel cable, the cabling must exceed 5 times the maximum gross load, encompassing sand ballast, the gondola, occupants, and all supplies. For hydrogen systems, electrical conductivity is required, while in ammonia systems, the cable length ensures separation from gas fumes. Venturing further into the theory of gas ballooning, a trio of knowledge domains emerges as paramount for competent gas pilots: physics, meteorological aspects, and the nuances of different lifting gases. Unpacking the physics, 4 pivotal factors dictate lift generation. The type of lifting gas employed, the amount of gas within the envelope, outside air temperature, and ambient barometric pressure. Understanding the intricacies of lift at sea level and altitude involves contemplating the weight differentials of various lifting gases and their dynamic responses to changing atmospheric conditions. The pressure ceiling, a critical concept in gas ballooning, marks the altitude where lifting gas expansion would fill the envelope entirely. Beyond this threshold, gas expulsion occurs, necessitating careful ballast management. Various approximations shed light on the effects of ambient pressure and temperature changes at different altitudes. Additionally, factors like the balloon's response below or at its pressure ceiling, the influence of gas temperature relative to ambient air, non-standard atmospheric conditions, humidity, and gas purity all contribute nuances to the complex dance of lift and descent in the vast expanse of the sky. In conclusion, the journey through the components and theoretical underpinnings of gas ballooning unveils a symphony of interconnected elements, where engineering, physics, and meteorology converge to orchestrate the graceful dance of these majestic vessels in the boundless canvas of the atmosphere.